So let's talk about a ramp, level ramp without friction. A ramp is simply a level piece of wood or steel or glass with an object placed on it and slippery enough where we can ignore friction. So the best way to do this would actually be to use that one-dimensional air track that I have in class set up on the side. If I tilted that, I would have a frictionless ramp. So here's the force diagram. The tilted line, angle theta with respect to the horizontal, is the ramp. The dot represents the mass. There are two forces acting on the mass, a downward force of gravity, mg, and it's touching the ramp, and the ramp exerts a force n perpendicular to itself. That's the normal force, of course. And since there's no friction, there's no force up the ramp uh, parallel uh, uh, parallel to the ramp, I should say, that is caused by friction. And so the first thing we do is we draw our coordinate system tilted relative to the ramp in such a way that the x-axis is parallel and the y-axis is perpendicular to the ramp direction. And n is already properly aligned in the y direction, but what we do is we take mg now and break it up into components that are either in the y or in the x direction. And so what we do here is, if this angle is theta, please satisfy yourself that you agree that this angle is also theta. Okay, here's a simple argument. If this angle is theta, this angle right here is the complement of that angle. And so this angle is the complement of that angle, and therefore this angle is theta. There's a simple argument for you. And so whatever angle this is the same angle. And so if I'm going to find the y component of mg, it would be mg times the cosine of theta. That would be pointing in the y direction, actually the negative y direction to be more precise. And mg sine theta would be the component of mg pointing in the x direction. And so using this scheme, I can write down down a Newton number 2 in the y direction of n minus mg cosine theta is equal to 0. Again, using the coordinate axes to bookkeep my signs, and a Newton number 2 in the x direction, which is mg sine theta is equal to m times a sub x. A sub x being the acceleration down the ramp. And so I should perhaps add a vector here indicating that this is the positive direction for a sub x. Okay, a couple of notes on this. First of all, again, a reminder that the coordinate axes are tilted with respect to the ramp, so that x and y are respectively parallel and perpendicular to the ramp. If we take the Newton number 2 equation and solve for n, we get n equals mg cosine theta. And so you will note that for any non-zero angle here, n is mg cosine theta. N, in other words, is less than the weight. In other words, as you tilt the ramp up, the normal force gets smaller and smaller as cosine theta gets smaller. Note that a sub x is down the ramp in the same direction as the net force, and it's equal to mg. The net force is equal to mg sine theta. And so if I take Newton number 2 in the x direction, and I solve for a sub x, it's very easy. You just divide both sides by by m, and so I would get a sub x is equal to g sine theta. Two special cases. If the ramp is horizontal, theta is equal to 0, and in that case, a sub x is equal to 0 meters per second per second. That's one extreme case, and the other extreme case is if theta is equal to 90 degrees, that would be equivalent to having the ramp vertically upwards. In that case, a sub x is equal to g times the sine of 90 degrees. The sine of 90 is 1, and the downward acceleration would then be g. this should make sense to you. And as you vary theta between these two extremes, between 0 and 90 degrees, you can make a sub x vary between 0 and 9.8 meters per second per second. This is historically how Galileo, Newton's predecessor, did his experiments on measuring gravity and understanding constant acceleration motion. So the next chart we will do, we'll discuss what happens if you put friction into this.